The purpose of this screencast is to provide some notes on static electricity and charges, how lightning works, and Coulomb's law. So in your workbook, you'll see a place where you can record some notes about what happens if you scuff your feet along the carpet and then touch a doorknob. You experience a small electric shock, and that's because what we've learned in class is that when you rub something with like fur or carpet or wool, you transfer some electrons or negative charges from the fur or carpet to the object, and so you are accumulating some negative charges into your body. And then if you touch a metal doorknob, those electrons move from your body to the doorknob. We know that metals are good electrical conductors, so those charges want to move from you to that doorknob. And that fast movement of the charges is what you experience as that small electric shock. So I encourage you to pause the screencast if you need to take down some notes in your workbook about that. There's a simulation which shows this too. It's called John Travoltage from the Fed website, so I'll quickly show you what that looks like. And it runs in HTML5, so you can use it on a mobile device or an iPad. But what you do is you can move his foot here and accumulate some negative charges. See, and then it's not even all that close to the doorknob, but you see the charges transfer to that doorknob. Alright, that's a fun simulation to show that concept. You may have seen this if you're filling your car with gas, that sometimes there are signs that you want to discharge by touching a post, or because you want to make sure that you're not creating any sparks from the static electricity that you might have on your body. It can be very dangerous. It can even, gas is very flammable gas, so that it could create a spark. And I have a little video clip about this. So here we see there's a girl who's filling her car with gas. And so you can see she's wearing some kind of sweater or something she got back in her car, kind of maybe rubbing up against the seat. Then when she goes again to touch, it starts on fire. And then she walks away, so we don't really get to see what happens after that, but hopefully, everything was okay. Well, that just kind of shows you what can happen if you create an electric spark. So always be careful about that. So how does lightning work? Well, it's caused by electric charges. There's some kind of separation of charges happening within the clouds or between the clouds and the ground. So you can see here there's some negative charges on the lower parts of the clouds, and they're attracted to causing some of the positive charges in the ground to come to the surface, or repelling the negative charges away from it. So things that are really tall, like these trees in the picture, or a tall house, you can see they're closer to where those negative charges in the cloud are. And eventually, these charges are able to connect to each other, and you get this electric charge transfer here called lightning. And there's a really good, about 3-minute video clip from National Geographic, so I encourage you to watch that if you're a little bit curious about lightning strikes and some fun facts about lightning. Scientists aren't entirely sure what causes these separation of charges within clouds, but they think it may have something to do with the updrafts and downdrafts going on between the different clouds. Alright, so I wanted to give you some notes about Coulomb's law. This is the statement of Coulomb's law, and also an equation form of the law. So we've seen a few things in class where we were experimenting with balloons and different materials to pick up pieces of tissue paper. And one thing that you looked at was, how does the distance affect the force or the number of pieces it could pick up, and how did the amount of rubbing affect it? And we see here that Coulomb's law can help us understand that a little bit better. This is saying that electric force, or the force between electric charges, is related to the charge on each object. So that's what Q represents. Q1 is the charge on object 1, Q2 is the charge on object 2, and D is the separation distance in between those charged objects. So that's the distance squared in the denominator. K is just a constant, so it's the same for all of the forces. So you can see that it's directly proportional to charge. If you have more charge, there's more electric force, and it's inversely proportional to the square of the distance. So if you have a bigger distance, you have a smaller force. If you're closer together, shorter distance, you have a bigger force, electric force, and you can pick up more pieces of tissue paper. So there's a couple of practice questions in your workbook. The first one is if you have two charged objects, and we're just going to say that they have a plus Q charge on each of them, and they're separated by a distance D. We want to kind of look at some proportional reasoning questions where if you triple the distance between them, make them 3 times farther apart, what happens to the amount of force that they experience? And so the way to do these problems is to first write down what is the initial force for this first situation. And so you would just write down from Coulomb's law, we had the Q, plus Q and plus Q here, and then the distance between them squared. So that would be the electric force for the first situation. And now if you want to have a new force, what we're going to change, we're going to keep the charges the same, but we're going to make the distance 3 times what it was before. So when you plug this in, you'll put 3D in the denominator and then have that quantity squared. And so if you work that out, when you have two terms here that are quantity squared, you can distribute that square between them. So you really have 3 squared and D squared in the denominator, so it's like 9D squared. And if you want to compare that to the force that we had before, you can see that this term is still in here, but the difference is that we have 1/9, and then we have the original force. So the way that you would interpret this is if you triple the separation distance of the charges, the force will be 1/9 of what it was before, so it'll be weaker. And if you want to represent that using arrows, you can see we drew arrows here for the force, the initial force. 1/9 of the force would look something like that. So a much smaller force when you change that distance. So here's another question. In this case, instead of making them farther apart, we're going to make them closer than they were before, so half the distance. So again, what you want to do is write down your initial force. We didn't change the charges at all, so we still have QQ over D squared. But the new force now, we're going to have 1/2 D in the denominator. And so if we follow the same procedure as before, you can see 1/2 squared is going to be 1 squared over 2 squared, which is 1/4. And we still have D squared. And you can think about this fraction however you want to think about it. One way to think about it is when you divide by 1/4, it's the same thing as multiplying by 4 over 1. So we end up with 4 times this term here, KQQ over D squared, which was our original force. So what this means is that if you half the distance in between the two charged objects, the force that they experience is going to be 4 times what it was originally. So if we want to draw that in terms of the force arrow, you can see it's quite a bit larger. You would take this and make it 4 times what it was before. So just by changing the distance a little bit, it's a squared term, it makes the force a lot stronger. So in this question, question 3, we're not going to change the separation distance. We're going to keep it at D, but then we're going to replace one of the charges. So one of the charges is going to have double the amount of charge as what it had before. So the initial charge, initial force is still the same as what we had before, but with the new force now we're going to have Q and then multiplied by 2Q. So you can bring that 2 term out in front and you have 2KQQ over D squared. So it's 2 times the force. So you can see by changing one of the charges we get double the force. But one thing that I wanted to point out is that even though these are two differently charged objects, one object has more charge than the other object has, the force that they experience is what we call an interaction force. You can see that both of the charges play a role in how much force is experienced. And we also learned about this in terms of Newton's third law. It's equal and opposite charges. So when you draw it, the force exerted on this charge by this one is the same as the force exerted on the 2q charge by the 1q charge. And they are both positive, so they repel each other, and that's why the force arrows are directed away. Alright, and then the last question, we're going to change another one of the charges, but this time we're going to have negative 4q on one of them instead of a plus q. So we still have the same initial force, but the new force, if we just talk about the magnitude of the force, we don't have to worry about the negative sign here. It's going to be 4 times what the original force was. But in this case, we had a positive charge and a negative charge, so they're going to be opposite charges and they're going to attract each other. So the force is going to be 4 times what it was before, but this force is going to be attractive instead of repelling. And so if we want to draw this, it's a little challenging to draw in this picture, but we're going to have 4 times the force on each of them pulling towards each other. So, and it's a little hard to see here, but this one's being pulled this way and this one's being pulled this way. Alright, so I encourage you to take some of these notes in your workbook and then let me know if you have any questions.